So we continue talking about the friction factor. I told you that the friction factor is needed to compute major loss or major head loss calculation. So major head loss, to recall, H major is the pressure drop across a straight pipe section divided by the density of the fluid, and this is calculated as the friction factor times V squared over 2 times L over D, where L is the length of the piping section and D is the diameter of the pipe. So this is D, this is L, the density is rho, and velocity is V, average velocity. So for this purpose, and a lot of experiments have been done. An experiment to calculate that pressure loss. So the experiment to measure pressure drop would be involving something like taking a section of a pipe that has a known length, it has known velocity, or the flow rate may be monitored downstream, and the flow rate divided by the area is calculated as the average velocity, and record the pressure difference between section 1 and section 2. So the delta P would be P2 minus P1. Knowing the fluid, we will know the density and viscosity, and delta P divided by rho is the head loss that we are looking for, and this is equated to F times V squared over 2 times L by D. If all the quantities are known or measured except F, it can be calculated. So experiments like these were carried out to tabulate the friction factor as a function of the Reynolds number. Okay, so Reynolds number, and then you have friction factor, and this is given in figure 8.20 of the book, and this figure is called the Moody chart. The Moody chart is basically an engineer's tool, which is a lookup table in the form of a graph that tabulates the friction factor value for different values of Reynolds number and pipes of different smoothness. So if in that flow, you will see that until about 4000, the friction factor versus Reynolds number is a straight line, which is true for laminar pipe flow. Okay, F is equal to 64 divided by RE. F is equal to 64 divided by RE. This can be derived from theory, although we won't go into that derivation, and this is valid for any, although this laminar flow expression F for laminar flow is valid for pipes of any roughness. Now what is roughness? If you think of the pipe walls, they are not really smooth. They have these minor ups and downs. We measure them with a mean squared roughness, and we divide that by the diameter. This is roughness of the pipe. And the figure 8.17 that we have in there, figure 8.20 has values of epsilon over D between 0.0001 to 0.05, which is a very rough pipe. And a very smooth pipe will have an epsilon of 0. Okay, and if you know to read the Moody chart, figure 8.20, you will first need to know the Reynolds number. you'll need to know the relative roughness, and if you have these two, you can read F from that chart. Okay, and we'll see this through examples. So to wrap up major losses, HL or H major is defined as F times V squared over 2 L by D. This is equal to the head loss delta P divided by rho across a pipe section. To get F, we use the Moody chart, for which you need to know the Reynolds number and relative roughness of the pipe. We will see these through examples. Moving on, I told you that in a piping system, the total head loss, which is the total pressure drop across the system divided by the density of the fluid, that is, if you have a piping system with flow entering here and the flow leaving somewhere downstream, the total pressure drop across the pipe is due to all the losses. That is, if you think of this as section 1 and section 2, you can write P1 plus half rho V1 squared plus rho G Z1 equals P2 plus half rho V2 squared plus rho G plus rho G Z2. This equation is valid, this is the Bernoulli equation, and it's valid if there are no frictional losses. We make a correction for frictional losses. We write P1 minus P2 plus half rho V1 squared minus V2 squared plus rho G Z1 minus Z2 should be equal to sum of all the losses, which we write as rho HL, rho times HL times G. Okay. Rho times HL times G. Now HL is what we considered as the head loss. It has units of length. It's a length, or it's the height of liquid column of density rho. And to calculate head loss, we split that into major losses, which we just saw, plus minor losses. Major losses are F multiplied by V squared over 2 times L over D. And our next item of discussion is the minor losses. Now, what are minor losses? You contrast them against major losses. This is pressure drop across a pipe due to friction. Minor losses are pressure losses or pressure drop in components which are sudden losses, like a 90-degree bend or a valve, 90-degree bend, a valve, a throttling device, and so on. It's a sudden loss, and if you have your piping system, let's say you have a pipe that runs for a length L1, and then you have a valve, okay, and then you have another section which runs for length L2. If you consider the whole thing, the whole assembly, including the two sections of straight pipes and one valve as your system, the delta P, or the head loss across the entire system, is the major loss across pipe 1 plus the minor loss across the valve plus the major loss across pipe 2. I've already given you the recipe to calculate these two terms. We are going to look at how to calculate the minor head losses across any component. We simply write the minor head loss, we simply write the minor head loss as the pressure drop divided by rho g. I have to make a correction here or note a correction in the previous few minutes where I talked about major losses. Previous few slides I talked about major losses. H major should have been delta P by rho g and not just rho like I did. Okay, note this correction. So H minor losses is simply written as a minor loss coefficient times V squared over 2G. Okay, it's simply written as V squared over 2G. Okay. KL is tabulated for a variety of conditions. That's a very big statement. For a variety of devices. You need to know what are all the common devices that you would encounter in your instrument or your flow system. And if you take a look at the textbook from figure 8.21, 22, 23, 24, 25, 24, 25, 26, and the list goes on. Okay, the list goes on until we reach, I think, around figure 32 and table 8.2. That is, the major losses are calculated from consideration of pipe flow using a combination of theory and experiment, whereas minor losses are almost entirely experimentally characterized, experimentally obtained. We have tabulations for KL for many engineering devices, engineering flow devices. If there is a device that you use but is not in the tabulated, or there is no data available for it, then you need to do experiments to obtain data. So wrapping up our discussion about losses, we talk about HL, which is the total head loss delta P divided by rho g. This is equal to the split into major loss and minor loss. The major loss is written as F times V squared by 2G. This is the G I left out, times L over D. And minor loss is KL times V squared over 2G. Okay. F and KL are tabulated. F is tabulated as Moody charts and KL is tabulated as loss coefficients for various devices. And we'll see examples how to use these KL values in problems. So the last two slides is a summary, and you should remember these formulas to solve pipe flow problems. Last thing, section 8.5. Section 8.5 is titled Pipe Flow Examples. You should go through them. It's based on the concepts that we just discussed, and we'll do some examples from them in class. Okay, but please come prepared.